Scaling to 1 million concurrent connections requires a complete departure from standard web server configurations. You must optimize every layer from the Linux kernel network stack and file system limits to the application memory management and distributed message architecture. We start by removing the default barriers that prevent massive scale. The primary bottleneck is the file descriptor limit. By default, Linux limits individual processes to 1,024 open files. Since every WebSocket connection is a file handle, your server will stop accepting new clients almost immediately. Update the security limits configuration file to allow at least 2 million descriptors. After increasing process limits, you must tune the system-wide maximum file handles. Use the sysctl command to set the file max parameter to 2 million. This ensures the operating system has enough resources to track every active socket and pipe across all running services without crashing the kernel under pressure. Port exhaustion occurs when a load balancer tries to open more than 65,000 connections to a single backend. The local port range is often restricted to 30,000. Edit the Internet Protocol local port range parameter to use the full range from 10,024 to 65,000.
Transmission control protocol connections in the time-wait state occupy ports even after the connection closes. This prevents rapid reconnection and drains your available port pool. Enable the time-wait reuse setting to allow the kernel to recycle these sockets safely, which is essential for handling high churn in connection attempts. 1 million connections will exhaust server memory if buffers are not tuned. Each socket typically allocates a read and write buffer. Default sizes of 200 kilobytes per connection would require 200 gigabytes of memory. You must reduce these buffers to the absolute minimum required for your specific message payload. Set the minimum and default transmission control protocol read and write memory values to 4 kilobytes. This allows the kernel to scale down memory usage for idle connections while still providing room for active data bursts. This optimization can reduce your total memory footprint by over 100 gigabytes at peak. The NetFilter connection tracking system maintains a table of all active network flows. Under heavy load, this table fills up, causing the kernel to drop incoming packets. You must increase the connection track max parameter to at least 1.2 million to accommodate your target connection count plus overhead. Load balancing for 1 million connections requires choosing between Layer 4 and Layer 7. Layer 7 balancers provide flexible routing, but consume significant processor power for every packet. Layer 4 balancing via the Internet Protocol virtual server is more efficient because it operates directly at the transport layer of the stack. To maintain visibility of the original client Internet Protocol address through a Layer 4 load balancer, implement the Proxy Protocol. This adds a small header to the start of the connection containing client details. Ensure your application server is configured to parse this header before the WebSocket handshake begins for authentication. Secure sockets layer termination is processor intensive. Instead of terminating encrypted traffic on your application servers, use a dedicated edge layer or hardware load balancer. This offloads the expensive cryptographic handshakes and allows your application cores to focus entirely on managing message delivery and active socket state transitions. WebSocket connections are stateful, meaning a client must stay connected to the same server node for the duration of the session. Use sticky sessions based on the client's source Internet Protocol address or a session cookie at the load balancer to ensure consistent routing to the correct backend instance. Distributing messages across a cluster requires a fast backplane. A single Redis instance using publish-subscribe can handle thousands of messages, but becomes a bottleneck as application nodes grow. Every message sent to Redis must be replicated to every connected server, which consumes massive amounts of network bandwidth.
To scale the message bus, use Redis sharding or a cluster of message brokers like NATs. By partitioning your message topics across different broker instances, you reduce the load on any single node. This architecture allows you to scale the delivery of messages horizontally along with your connection count. Heartbeats are required to prevent firewalls and load balancers from closing idle connections. However, sending a heartbeat every 30 seconds to 1 million clients creates a constant stream of 33,000 packets per second. You must carefully tune the frequency and payload size of your heartbeat pings. Apply jitter to your heartbeat intervals to prevent the thundering herd problem. If all clients connect at once and use a fixed interval, they will all send pings at the same time, overwhelming your processor. Randomizing the interval by several seconds spreads the load evenly over the entire time window. If a server node fails, thousands of clients will attempt to reconnect immediately. This creates a massive surge in connection requests and encryption handshakes. Clients must implement exponential backoff, which increases the delay between reconnection attempts to give the system time to recover and stabilize from the failure. Application-level authentication should be fast. Avoid doing complex database queries during the WebSocket handshake. Instead, use signed tokens, like JSON Web Tokens, that can be validated locally, or check against a fast in-memory store like KeyDB. This reduces the latency and resource consumption of new connections.
Garbage collection in managed languages can pause all execution threads. During a long pause, the server stops processing heartbeats, leading to massive client timeouts and a reconnection storm. Use low-latency garbage collectors and optimize your memory allocation to keep pauses under 10 milliseconds, even under heavy load. Node.js is single-threaded, which limits its ability to handle high packet rates on multicore systems. Use the cluster module to spawn one worker process per processor core. This allows your application to share the incoming connection load and utilize the full throughput of the server hardware. Memory efficiency is the most important factor in choosing a WebSocket library. Libraries like UWS are written in C++ and provide a thin wrapper over the kernel sockets. They use significantly less memory per connection compared to higher-level frameworks like Socket.io or standard libraries. Slow consumers are clients that cannot process data as fast as the server sends it. The server must buffer these outgoing messages in memory. If 1 million clients are slow, your server will run out of memory and crash. You must implement backpressure to drop messages or disconnect slow clients. Configure your network interface card to distribute packet processing across multiple processor cores. By enabling receive-side scaling, the hardware hashes incoming traffic and sends it to different interrupt queues. This prevents a single processor core from becoming a bottleneck during high-volume packet ingress and egress.
Bind network interrupts to specific processor cores using SMP affinity to avoid cache thrashing. When interrupts move between cores, it forces the processor to reload data into its local cache, which slows down processing. Locking interrupts to dedicated cores improves the efficiency of your packet handling at extreme scales. The initial transmission control protocol three-way handshake happens in the kernel backlog. If the backlog is too small, the kernel will ignore new connection attempts during a surge. Increase the maximum SYN backlog and the listen backlog to at least 5,000 to handle sudden bursts of clients. The WebSocket handshake uses the Hypertext Transfer Protocol upgrade header. You can save memory by reducing the allowed size of these initial headers. If your application does not need large cookies, setting a strict limit of 4 kilobytes per request prevents bloated requests from wasting precious server memory resources. Zero-copy networking allows the operating system to send data from a buffer directly to the network interface without copying it to user space. Using the send file system call reduces processor usage and memory bandwidth, which is critical when you are streaming data to millions of concurrent clients simultaneously. Monitor your system in real time using tools like the socket statistics command, also known as SS. This tool is much faster than the old netstat for inspecting the state of millions of sockets. Use it to check for queues that are filling up or connections stuck in closing states.
Kernel memory for sockets is allocated from slabs. Use the slab-top command to monitor how much memory is consumed by the transmission control protocol and socket caches. If you see high memory usage not reflected in your application process, the kernel is likely holding too much memory internally. Verify your scaling strategy by running distributed load tests. A single load testing machine will run out of ports at 65,000 connections. Use a tool like Locust, orchestrated across 20 or more cloud instances, to simulate 1 million clients and identify hidden bottlenecks in your entire stack. When testing, monitor the processor usage of the soft interrupt handler. If it consumes a large percentage of a single core, you are hitting a packet processing bottleneck.
You may need to optimize your network driver settings or use higher performance network interfaces with advanced offloading features to reach your goal. Network latency affects how long buffers are held in memory. In high latency environments, data stays in the send buffer longer, increasing total memory pressure. You must account for this when calculating your total memory requirements and potentially increase your buffer size slightly to maintain throughput over long distances. Use a monitoring system like Prometheus to track the number of active connections per server node. Visualizing these metrics in a dashboard helps you identify unbalanced load distributions across your cluster. If one node has significantly more connections, your load balancer hash function may need adjustment for better distribution.
WebSocket frames have a small overhead of 2 to 14 bytes. For small messages, this overhead is a significant percentage of the total data sent. Batching multiple small updates into a single WebSocket frame can improve network efficiency and reduce the number of packets the kernel has to process every second. To achieve high density, avoid using features like per-message compression unless absolutely necessary. Compression requires the server to maintain a stateful window for every connection, which consumes several kilobytes of memory. Disabling compression allows you to fit significantly more connections on a single server with limited memory resources. Use Linux control groups to isolate the resources used by your WebSocket server. This prevents the application from consuming all system memory and causing the kernel to trigger the out-of-memory killer. Setting hard limits on memory and processor usage ensures system stability, even during unexpected traffic spikes. Compare the overhead of transmission control protocol keep-alives versus application-level pings. Kernel-level keep-alives are more efficient, as they do not wake up the application process. However, application-level pings are better for detecting dead logic or frozen threads within your server code that the kernel might ignore. Implement rate limiting for new connection handshakes at the edge. While your server can hold 1 million connections, it cannot process 1 million handshakes per second. Limiting the rate of new connections prevents a surge from overwhelming your processor and ensures that existing connections remain stable and responsive. For global scale, use Anycast Internet Protocol addresses to route clients to the nearest available data center. This reduces the latency of the initial handshake and spreads the 1 million connection load across multiple geographic regions, providing both better performance for users and higher resilience against regional outages. Achieving 1 million concurrent connections is the result of systematic optimization across the entire stack. By tuning the kernel, minimizing per-connection memory, and building a sharded distributed architecture, you create a system capable of massive scale. Monitor your metrics constantly and always test for the next bottleneck.